Okay, so we're asked now to look at some examples here to determine whether an alternating series converges. So first things first, with this series here, sorry, sequence. Sum of k goes from 1 to infinity, negative zero point 0.8 to the k. Let's think of this first as an alternating series. So first things first, I have that negative inside raised to a power. So I'm going to pull that out so it's on its own. So that's my alternating series. And then I have that 0.8, which can be written as the fraction 4/5 to the k. Now, we can see first off that this 4/5 to the k term, as k gets bigger and bigger, this underlying a sub k sequence, right? That's just going to keep going to be like 4/5, then 4 squared over 5 squared, 4 cubed over 5 cubed, 4 to the 4th over 5 to the 4th, and so on. So we very quickly notice that this sequence, 4/5 to the k, is definitely decreasing, because as you raise 4 to the k and 5 to the k, 5's growing faster than 4 is. So, right, so therefore this 4/5 to the k is actually a decreasing sequence. So we check off that first condition, it's decreasing. So the second question is, does the limit go to 0 as we go to infinity? That's the other condition we need to check. Limit as k goes to infinity of 4/5 to the k. So to work this out, we translate it over to an exponential. Right? This is something we encountered before. We were dealing with limits. Right? This is the same as e to the ln of 4/5 to the k. Right? Because remember, e to the ln cancels out. And so simplifying, this would be the limit as k goes to infinity of e to the ln of 4/5 times k. But we know that ln of 4/5 is negative. So this is e to a negative power, meaning that we could really write it as 1 over e to the negative of that stuff. Right? So we have 1 over e to a positive power. And so then as k goes to infinity, 1 over e to a positive power times k is going to go, well, e to the positive power is going to go to infinity. And 1 over that would go to 0. And so therefore it converges. So we've checked off our two conditions, right? The underlying sequence is non-increasing. In fact, it's actually decreasing. And the limit goes to 0. So by the alternating series test, the series converges. And that's seen to this problem. But we can actually compute this one directly. We actually could have gotten this resolved another way, because this is a geometric series. This is a geometric series. So we know since the ratio, the absolute value of the ratio is less than 1, we know that this would also converge. So we can actually go a little further with this, and this is just to kind of review. This is not a part of this problem, but just to kind of review this idea. Since it is geometric, then we know that the series as k goes from 0 to infinity of negative 4/5 to the k is actually equal to a, which is 1 over 1 minus negative 4/5. 1 minus a negative 4/5 would be 1 plus 4/5 would be 9/5. Reciprocal of that would be 5/9. So we know that series, the series starting at 0 to infinity, converges to 5/9. Our series then, which is the series that starts at 1, so in other words, it's leaving off the first answer, which is a 1. It's leaving off the 1 from the original series. We can then say our series actually converges to 5/9 minus 1. Right, subtract off that first value. And so our series actually converges to -4/9. Again, because it's a geometric series, we can use that formula to talk about its convergence when we start at 0. And then we can just strip off the values that we excluded from our series up above. And so our series actually converges to -4/9. And again, that's because it's geometric. So this is just kind of a little add-on to the problem here. A little add-on to the problem just to review our geometric series ideas and kind of bring them back into play. The actual question is resolved here though, right? Since it is the underlying sequence is decreasing, which of course means it's not increasing, then, and the limit goes to 0, our series converges.